Excuse me. Can you see my slide?
Yes, we can see. Yeah.
Oh, okay.
We can see, and you can start. You're welcome.
Okay, thank you. So I first like to thank the organizers for the invitation to present my result in this conference. This is a joint work with Jindong Lin at Taiwan. Here is the outline of my talk. I first introduce a multi-term time fractional evolution equation, which I will abbreviate by TFEE. Then I will present the main result, which is the classical unique continuation property for the TFEE. This classical unique continuation property will be abbreviated by classical UCP. For this main result, there is some regularity assumption for the solution. The solution which can have the classical UCP. So I will discuss about the regularity assumption in view of the regularity of the forward problem, which has been studied by several people. The rest of my talk is about the outline of the proof. So let me start introducing the TFEE. The interval 0t, this is a time interval, and omega is a domain in Rn. And I'm going to consider this operator applied to U, where the coefficient ajk is a function in this function space. And then I think you will wonder, what is this guy? This B infinity of R 1 plus n. This is a set of all functions in C infinity R 1 plus n bounded together with their derivatives. Why I'm going to use this kind of a function space is because this is a very convenient for using the characters of pseudo differential operators. That the operator L is assumed to be strongly elliptic. That is, I'm assuming this symmetry for the AJK, and also the positivity for the matrix AJK, given by this inequality. Now, I'm going to introduce Qj and also alpha j. For j between 2 and m, Qj belongs to this function space. And the Q1 is taken to be equal to 1. And for alpha j is indices labeled in the descending order. And they are in between 2 and 0. And for alpha 1, I just denote by alpha. Okay, so what is the TFEE? It is given as follows. So there is the operator L here, and also there is the T derivatives. But the T derivatives here are of fractional order. Okay. And L1 is just a linear partial differential operator of order 1 with C1 coefficients. And the time derivatives are defined by this formula. This one is for the case k equal to 1 and 2, and alpha is between k minus 1 and k. And for alpha equal 1, this is just the usual t derivative. And here the h is the Heaviside function, and delta y is the Dirac delta function supported at y. You may wonder whether we can define this kind of a convolution, but our u, which will be taken from this function space, I will define this function space later, can be assumed as a right-sided distribution in our argument. So the above convolution can be defined. Okay. Moreover, if this derivative can be defined, the previous alpha order t derivative, this is just the Caputo derivative given as follows. Okay, now for temper distribution V, I define this function space as follows. The V is in this function space if and only if the following, the square of this norm is finite. Okay, and where this hat is just the Fourier transform with respect to x and t. Okay, this is the how this function space is defined. Now for this set, I just define this function space as the restriction of this function space to this set. It is well known this function space has this kind of description. Now it's ready to present our classical UCP. It is stated as follows. Let U be a solution of TFEE, and also U belong to this function space. Then if U equals 0 in a subdomain of this domain, then U equals 0 in this whole domain. Okay. So this is our classical UCP. Let me compare this classical UCP result to our previous theorem. Our previous theorem is stated as follows. Let U be in this function space. This is the same as before, and it satisfies the TFEE. But there's another condition that the U is supported on T larger or equal to 0. This additional assumption, we call it the support condition. Then if U equals 0 in a subdomain of this set, then U will become 0 on the whole of this set. Okay. The precise meaning of the support condition is as follows. That is the 0 extension of the U across T equals 0 belong to this function space. Okay, I would like to give an incomplete list of known results. For the classical UCP, if the time fractional derivative order is just 1/2, and for the one space dimensional case, Xu, Chen, and Yamamoto gave the first result. And this result was generalized to a higher space dimensional by Chen, Lin, and myself. But this is still the time fractional derivative order is 1/2. For more general order for the time fractional derivative, the order alpha is between 0 and 1. but for the one space dimensional case, the classical UCP was given by Lee Yamamoto. Also, the stability of the lateral Cauchy problem for alpha smaller than 1/2 was given by Lee, Wan, and Yamamoto. Under the support condition case, Lin and myself gave the classical gave the UCP for the single term slow diffusion case. Means that is alpha is smaller than 1. And also for the multi-term slow and fast diffusion case, that is alpha can be between 0 and 2. These were given by Lin and myself. Also, there is another kind of UCP called the weak UCP. That is the UCP for the solution for the initial boundary value problem having a homogeneous boundary condition. The statement is the same, except that the solution must be a solution of the initial boundary value problem, satisfying the homogeneous. Discuss about the regularity issue of the solution for our classical UCP. I will consider this regularity issue for the case that the boundary condition is just a homogeneous Dirichlet boundary condition. And also, the equation only have a single term, time fractional derivative. And also the equation doesn't have inhomogeneous term. So for this discussion, I will consider the solution given in Kubica, Lizweska, Yamamoto's book, and also the well-known paper written by Sakamoto and Yamamoto. Okay. For the first one, this KRY book, it's discussed for the time-dependent elliptic part. And for the paper by Sakamoto Yamamoto, this is discussed for the time-independent, formally self-adjoint elliptic part case. Okay. Please remember this abbreviation KRY and SY. Okay. Then for the solution with the initial data in this function space belong to our function space, if alpha is between 1/2 and 1 for the KRY case, and for the SY case, also it belongs to our function space, alpha is between 0 and 1. For this one, if the initial data is 0, then also for the alpha between 0 and 1, their solution also belongs to this function space. Okay. Furthermore, and also the coefficient of the time-independent formally self-adjoint elliptic part of the equation and initial data with the compatibility condition. They also discuss for the Neumann boundary condition case. Then the recent paper by Kyan and Yamamoto, their solution belongs to this function space for all the alpha in the interval 0, 2. So these are the discussion I made for the regularity assumption we are putting for our solution. Okay, so another reason why we are using this function space is that this function space really fit to the scaling property of the principal part of the TFEE equation. And also this function space is a very convenient function to use the pseudo differential operator calculus for the TFEE. Okay, our classical UCP theorem will follow from the following theorem too. First, let the B1 belongs to omega. Here, BR is just the ball center at the origin with radius r. And also let the U belong to this function space, and it is a solution of TFEE. Then if U equals 0 in this set for some R smaller than 1, R is a positive real number smaller than 1, and let the Z be a boundary point of BR. Then there exists R hat smaller than R such that the U equals 0 in this set. Let me give you a picture. So we have a BR, and we take the point Z of at the boundary of this BR, and then there is some small ball we can take such that the solution U can be also 0 here. Okay. So how to prove this? Let me give a schematic outline of the proof of this theorem too. We will use two kinds of Homogeneous transformation. The Homogeneous transformation will be abbreviated by H-TRF. We will use the usual one and also a special kind of Homogeneous transformation. For this transformation, we will adopt a Trepp's argument, and also also we will use a global coordinate transformation for the special Homogeneous transformation case. And then we can get associated local Kalman estimate. And then for the case we use the usual Homogeneous transformation, then we can just argue in a standard way to get some UCP. And for the case that when we use the special Homogeneous transformation, we have to also use an iterative argument to get some UCP. And combining both the UCP, we can get the classical UCP. The details is very technical, and I will try to explain you as much as I can in the remaining time. Okay. First, I state the proposition 1. Okay. That is, if U belong to this function space and assume U is a solution of TFEE in this set, and also U equals 0 in this set, and then for any Z hat, which is the point of the boundary of VR, there exists R tilde smaller than R, and also T1 and T2, which have this T over 2 in the interval T1, T2, okay, such that U equals 0 in this set, okay. So I will next show you the outline of the proof of this proposition 1. So first, without loss of generality, we can assume that the Z hat is given in this form. Okay, and now consider the Homogeneous transformation, which is given in this form. Okay, here the C is a constant, and we will fix this constant. C will be small, larger or equal to 1. This Tx will be called a Homogeneous coordinate. Okay. Since we have a time fractional derivative, and if we consider the Fourier transform, the symbol of this time fractional derivative, it may have a branch point, and I don't like that. So to avoid that branch point, I will conjugate our operator of the equation by this function et. Okay, so I conjugate in this way. This is our operator, and I will denote the conjugated one by a capital P, and also to relate its symbol, I will also write using the small p of Tx dt dx in terms of the Homogeneous coordinate, where dt is minus I times partial t, and dx is minus I times the nabla x. Now I'm going to define p psi for the V taken from V. V is just a compactly supported distribution in this set as follows. So p psi b is given by this formula. And what is this psi? Psi is a Kahneman weight function given as 1/2 of xn minus 2 times x squared, where x will be determined later. Anyway, x is a fixed constant which will be determined later. Okay. The p psi, even having this kind of absolute of sigma, which you may think that this is creating some singularity, but this p psi admit very nice pseudo differential operator calculus. First, we consider this kind of a scaling for a large rho. Then we can define the principal symbol of p psi denoted by p tilde of psi. And then this principal symbol has the following estimate for its Poisson bracket. This is the Poisson bracket. And this one has the estimate from below. Here, this symbol means this is just a modulo positive constant of the usual. This case is like smaller or equal. And this inequality holds for under the condition that the p tilde of psi equals 0 and the x prime and xn satisfy this condition. So the x I mentioned here, which will be determined later, is determined by this lemma. I'm going to take this x as the x here. Okay, and then once having this estimate for the Poisson bracket, we can have the sub-elliptic estimate for the p psi. To state that one, we introduce HDC. This is given in this way, and also lambda alpha s given in this way, and also consider the set U, which is given in this way. Okay, with some positive constancy. Then there exists a small z0, a positive z0, such that for any u taken from this function space, we have this kind of sub-elliptic estimate. The first inequality for the case alpha is smaller than 4/3. And the next one is for alpha larger or equal 4/3. Okay, then how to get the Kahneman estimate? The Kahneman estimate can be derived by just taking U in this way. Okay, and then we can interpret the previous sub-elliptic estimate into a Kahneman estimate for the V. So we can have this kind of a Kahneman estimate. Okay. Now going back to the proof of our theorem, that is the localized version of our classical UCP. Okay. From the proposition 1, sorry, I forgot to say. Well, once having the Kahneman estimate, then the proposition, the proof of the proposition can be done by a standard way. So we have the proposition 1. Okay. Now having proposition 1, let's go back to the proof of theorem 2. Okay. By proposition 1 and some diffeomorphism, we can consider in the following setup. So the equation can be given in this way, and also the U is 0 for T and Y, T in this interval, Y in this set, where R1, RR is defined in this way. And also U is 0 for T in this, and Y is in R1 minus. R1 minus is this one. Okay. So from now on, we consider in this setup, and then we will consider the following diffeomorphism. Okay. Okay. We will map R1 to Rn. And this mapping Y tilde is given by this formula. Okay, then the previous this 5 will be transformed to this set of equations. Okay. And now consider U hat defined by theta t times U, where theta t is a smooth function having this property. And then it's easy to show that U hat will satisfy this set of equations. And then by previous argument, we can say U hat, previous theorem, we can say U hat equals 0 for all T. Okay. So that going back to the original U, U is equal 0 for T in the interval T1 and T. And then to finish the proof, we only need to prove the following proposition. Okay. First, assume that U satisfy the U in this function space satisfy this set of equations. Okay. Then there exists R2 small such that the UT Y tilde is 0 in this set. Okay, so this one is also the proof of this one is very technical. Here we need to use some iterative argument. How to say? Well, we will prove that the U will become 0 using the iterative argument. First, it will become 0 here, and then next 0 here, etc., to get the conclusion. Okay, this is all. Thank you for your attention.
Thank you very much, Professor Nakamura. Any questions? Or remarks? There is no questions. Maybe we need some time to understand your talk more carefully. And thank you very much once again.
Yes,
And,
thank you.
Yes, please stop sharing your screen. And we invite the next speaker.
Okay.
It's Dr. Alexey Pinenko. Yes, we're hearing you very clear. Could you please share your screen? And it's a talk with, joint talk with a group of authors. And Alexey, please, 30 minutes.
Thank you very much. I'll start at 12:15 schedule. Okay, so we shall wait for 6 minutes. It's still a scientific council in the institute, so we shall wait.
Yeah, sorry, we should start at 12:15, Novosibirsk time. Yes, 5 minutes waiting.
Okay, dear colleagues, let us start. I would like to talk about second part of our bigger picture, and it will be about using different types of measurements. And as you know, for example, the air quality can be measured by very different means. And these measurements can have different precision, can be localized differently. We can measure different chemical substances and so on. And in order to understand a complex phenomenon or something, or observe some territory, or for example, understand the air quality of the city or some other object, we have to somehow consider this data in some fused ways. So we have to jointly consider various sources of data. But data itself, it has no meaning. It has the meaning to the data must be somehow prescribed. And a good way to interpret measurement data is to use mathematical models. For example, they can connect our data, like concentration of some substances in the air, to the, for example, sources of pollution. And keeping in mind this link, we can try to evaluate different types of measurement system, to compare them, and to find out, for example, which measurement system is preferable if we need to, for example, design another one. And as the topic of our work is working with various types of data, then we have to somehow develop an inverse modeling approach that allows to work with very different measurement data. And as the basic inverse modeling task, we shall consider the source identification problem using the measurement data. Also, when we are talking about comparing different measurement systems and different scenarios, we have to develop a set of estimates. For example, they can be ranged with respect to accuracy, computational intensity, or information required to obtain this estimate, to evaluate this estimate. And we will do this within our inverse modeling framework, which we called the joint ensemble framework or sensitivity operator framework. Yesterday, I was talking about the use of this framework to identify parameters in production loss systems, namely in chemical kinetic system. Here we have a bigger model. So here is the non-stationary advection diffusion reaction model. These are the terms that are responsible for transfer. These are terms are responsible for the reaction in so-called loss and production form. We have a number of species, NC, and the model is non-stationary in time. Also, there are initial and boundary conditions as usual. And for the loss and production operators, here we will talk about polynomials. And all the parameters of our models are divided into groups. So the first group is called known parameters. Like here, these are the wind speeds or diffusion coefficients and the uncertainties. In this case, these are sources of emissions. And we set the direct problem operator this way. So it maps the source, emission source, to the state function. Then we have measurement operators of different kind in this work. Yesterday, that was just point-wise concentration measurements. Today, we will talk about different types of measurements, and we state the inverse problem. We have this measurement operator that maps the state function corresponding to some exact value of the uncertainty function to the measurements, and we have some noise. And this is the problem. And the problem is to estimate this uncertainty function from the measurement data. Okay, the cornerstone of the approach is so-called sensitivity relation, which connects the variation in the uncertainty function. In this case, these are the sources in the right-hand side, to the variation of the state function with some weights, h cap and h lowercase. And these weights are under our control, and they act as the sources for the so-called adjoint equation for the model, which has the structure similar to the equation in variation for the direct problem, but it's solved in the reverse time and is linear with respect to this function, sources h. And the solution of the adjoint problem is used to obtain the sensitivity function, which weights the variation in the uncertainty. And conventionally, it is used to evaluate misfit cost function gradients. So here we use a slightly different idea proposed by academician Barchuk. And he proposed for any element of measurement data, consider its sensitivity relation and collect the sensitivity relations to a single relationship. But what if we deal with the images of high dimensionality? So how can you deal, for example, calculate the adjoint problems for every pixel of our image? It's pretty hard because you have to solve very many adjoint problems. Then you have to somehow to aggregate this data. And in order to do this, we introduce the image to structure operator that does this aggregation and depends on some set of projection functions on the measurement data. And then, following the idea, we collect them to a single sensitivity operator, which can be evaluated in parallel. And then we have the parametric family of quasi-linear operator equations. So what is good about this family? The first thing is that by controlling the projection function set, we control its dimensionality first. Second, we can control, we can filter some noise from this, from the data. Then we can evaluate it in parallel. And also, it's not just a single equation, but it's a family of equations. And we will use it to solve and to analyze the problems in what follows. Okay, so this is a short introduction to the inverse modeling framework. It intersects with yesterday's talk, and now let's go to the part that is new. So here is a scheme how we model, how we use this framework to model different inverse modeling task. So we start from the formulation, we have the sensitivity relation, define the adjoint problem, define the uncertainties. Then we have the ensemble defined by the projection function set. And then we have a family of quasi-linear operator equations. We can solve it. I also talked about yesterday. We use a Newton type method to do this. You can take any method you want, actually, but we take Newton type 1. And what I will talk in details is the analysis based on the sensitivity operator of our problem. What about it? So if we have heterogeneous measurement data, then we have to present it in terms of the projection functions. Here you can see a different type of projection functions corresponding to different types of measurements. So for example, if your measurement site measure time series, you have this projection function of some species, for example. If you have pointwise measurements by ship, by aircraft, or by car, measuring some points of time and space, then you have pointwise measurements with the corresponding projection functions. Integrals are something like snow, measurements in snow, or bio measurements, and so on. And of course, picture type snapshot measurements, so defined by its projection function set also. And in order to fuse different data types, we simply have to join corresponding adjoint ensembles. Of course, a listener can say that it can also be done within the variational approach when you just sum different terms of the cost function corresponding to different measurements. So what's the special about it? So and here we join the joint ensembles corresponding to individual measurement times. What is special? I'll try to explain. Okay, so first is pretty common. So we can analyze a monitoring system using some scenarios. So usually we know what we want to measure. This work is a part of a large scientific project about Baikal Natural Territory, when we have to monitor it by different means. And the scenario is connected to this project, of course. So we have a 3-day-long scenario. We consider pretty small but significant NOx ozone cycle as a transformation model. And in the scenario, we think that the sources emit NO. So we know it's the emission of, for example, traffic and industry, and we measure ozone. So we do indirect measurements here. So we have not just difference between sources and measurements within space, but we have difference within the chemical substance that is used for measurements and for emissions. And we took the monitoring sites from the some of the Ross hydromet sites acting in the region, and we produced the exact scenario where the emission is proportional to the population of the cities in the region. Took as the as a main source the emission rate of Irkutsk according to the literature, and we tried to reconstruct first of all, and we divided the set monitoring sites in 3 groups. So first group, blue, take pointwise measurements in space and time. Red crosses collect time series, and triangles gather integrals over the time period. And let's look how this this data can be used to estimate the sources. We can see here that for different type of measurements, individual measurements, we obtain the following reconstruction. This is the exact one, and this is the reconstructed results. So we can see they're pretty different. And if we collect them, consider composite measurements, then we will reconstruct this bigger picture. Of course, this quite a expectable behavior. So we take more data, we obtain better picture. But yesterday I was talking about a scenario when it is not the case actually. So it's expectable, but it's not necessary. It should be this way. Actually, you can refer to yesterday's YouTube recording to look more in more details when it can happen. But here it was expected. And this is the error with respect to computation time. So this is the error of composite data, and this is the errors for different type of measurement data. We see that we have this synergistic effect here, observable. Okay, what if we take another configuration of sources? So here, this is what we considered previously. This is the equivalent sources when all the sources are emission rates are identical for any city in the region. So this is what we obtain. You see, we obtain some artifacts here. Also, and a scenario when all the sources are in Irkutsk. And so what we construct here? So we near the Irkutsk, in the nearest grid point to the city of Irkutsk, actually. And what we construct here? So we construct the source, and also there are some artifacts here. You can see. Okay. So, but what if we need to consider different inverse problem statements, or, for example, to optimize the measurement system? The first solution is just solve the inverse problem for any configuration and compare the results as I showed previously on the previous slide. But if we look at the time scale of the solution, we can and measure the solution of inverse problem in the solutions of the direct problems, we can see that the solution of the inverse problem can take thousands of inverse problem solutions. Sorry, the time of inverse problem solutions, direct problem solutions. So, and if your direct problem is solved for a week on the supercomputer, then you probably won't be able to use it within the framework. So, but we somehow have to optimize our measurement system. Okay, what are the possible approaches? So the first approach is to improve the technological context of your programs. So this is the picture of our IMDAF framework, Inverse Model and Data Assimilation Framework, which is written on C++ and does the parallelization with OpenMP. Post-process and the pre-process are done in Python, but this computation kernel is on C++. And the next step is to we measured the parallelization acceleration study here. So we obtain right now the acceleration in 15 times with respect to single-threaded application. But we are considering the movement to MPI actually because of the problem structure. So basically, it should be parallelized in a more inefficient way. So this is the first approach. I won't talk about it here anymore. And the second approach is to somehow deal with the sensitivity operators. And the first idea is the first-order sensitivity operator analysis. So we can basically consider this sensitivity operator, which is nonlinear. We can consider its linear part, for example, in the initial estimate of our sources. In our case, it's just a zero emission sources. And if we look at the quasi-linear problem, then we can see that and look at it as at the linear problem, then we can use the linear tools to estimate the information content that is left in the measurements. So we can basically consider the kernel of the sensitivity operator, and it describes the information that is lost when we get from the source to the measurement data. We can quantify it by the projector to the sensitivity operator kernel and orthogonal complement of this projector. And in the ideal case, it should be equal to identity. It means that all the information about the source is still in the measurement data, and we can reconstruct it. And the first estimate is a projection-based estimate. So we just take the difference between the identity operator and this projector and apply it to the exact solution. If we need to optimize the measurement system, then it's possible, because we plus minus know what we want to measure. So we can use this estimate for this inverse modeling task. Another approach is to consider what we call the sensitivity statistics. So, for example, so-called elimination functions are the diagonal of this projector. So basically, if the projector is identity, then on the diagonal you should have ones, and then you can measure the difference between what you really have on the diagonal to the ones you should have here. And you can do this on the pointwise basis, because each point of this each point of space corresponds to some line of this projector, and you can you can say that some line of this projector's matrix, I should say, and we can calculate the statistics. Looks good, because here you have to analyze a matrix that has a dimensionality of number of unknowns by number of unknowns, which is in our case is something like 3040 by 3040. Okay, which is pretty hard. And in case of diagonal, you should consider only 3,400, which is equivalent, which can be put on your geographical map and look at it visually and show to anyone. Okay, but is it good? Let's look at the corresponding experiments. So this is this more small picture of the sensitivity operator-based analysis. So we start from the exact solution, exact sources. We obtain the reconstructed solution by the inverse problem solution itself, and we have to take 85 iterations of our Newton type algorithm. But if we look at the projection type estimate, in order to obtain this estimate, we have to make only one iteration. So we have to only once estimate the sensitivity operator, and we can project our exact solution and see what we have. We can see that these solutions are quite similar, but it's almost 200 times cheaper. Okay, what about elimination functions? This is one for the heterogeneous measurements. When we take all the measurements like pointwise and snapshot type, the picture is quite good. We have ones near the measurement sites here. We have less than one in the other regions, but we still have the picture here because we have a final moment snapshot in this scenario. But what about the quantitative estimates? So here is the quantitative estimates of errors. The red one is so-called empirical, which you obtain by solving the inverse problem. And this two blue and green are estimates we obtained by the projection. So exact projection is the operator which takes the initial guess And the exact solution and the neat projection is the estimate that takes only initial guess here. Okay, we see that these estimates are quite similar. And here are the singular spectrum. Actually, I should say that I don't know how to estimate this measurement system, compare them by the singular spectrum, because they, for example, can intersect and so on. So it's not that easy. Singular spectrum sensitivity operator. Okay, and these are the reconstruction-based estimates. Sorry. Come on. Reconstruction-based estimates for individual measurement types. So we see that, come on. We see that they are pretty similar. So empirical reconstruction and projection-based estimate of this reconstruction. Okay. What about the presentation lives with its own life? What about the statistics of the operator? The pictures are too heavy. What about the statistics? We see here, these are the elimination functions for individual measurement types. We see that they look also good. For the measurement sites, there are ones, and there are less than one for measurements far from measurement sites, and zeros that are invisible here. And this is the estimates based on this so-called statistics. So here we can see that they are there are different statistics, but the main idea is to measure the difference between the identity and this, the identity and the projection operator here. Okay, but what about the complete picture? So how we can summarize it? One more experiment is the homogeneous measurement networks. So we now collect the different experimental data to summarize it then. So here is the homogeneous measurement networks when every site of our network collects a specific type of data. So point-wise measurements, reconstruction of point-wise measurement based on point-wise measurements, on time series, on integrals, when we collect only snow, for example, in all the measurement networks, and the snapshot reconstruction. Okay, some more statistics. So the time series type, empirical reconstruction, and its estimates. We see that we, and from the bottom to top, we have the increase in the measurement, in the number of data here. And we can see some monotonic increase here in our estimates. But what about the summary? We show this on the following scatter plot. So we basically put the empirical reconstruction estimate on this axis, and put the corresponding estimate on the other axis. And in the ideal case, we should have the diagonal here. And for the projection-based estimate, and different points correspond to different experiments. We have 35 numerical experiments with different configurations, different conditions, and so on. And for the projection-based estimate, we almost have the diagonal, but it takes the exact solution here. In the next set of estimate, these are statistics. It takes only exact locations. So we measure the statistics in the locations of our cities. We can see that it's not that diagonal here. We can tentatively say that it's monotonically decreasing in some way, but still it's not that easy to interpret like this one. And this statistics, it takes nothing, so it knows nothing about the location of sources. It's even harder to interpret, actually. And finally, we can conclude that the projection-based estimate showed turns to be the best one estimate that can be used to evaluate different measurement systems. For example, composite one and heterogeneous ones. And other types of estimates, they need different consideration, further studies to say if they're good or not. Okay, this is the summary. I briefly told about it. So we looked at the use of sensitivity operator approach to analyze heterogeneous measurement systems and did the experiments how we can estimate the solution of inverse problem before its solution. These are the references. This work we expected to be published next week in the atmosphere, and this one should be published next year. Okay, thank you very much. Thank you for your attention. That's it.
Thank you very much for your talk. It's time to have a lot of, no, not a lot of, but time for questions. Any questions or remarks to Alexei? Maybe I have a little questions about parallelized. You said about that you need to MPI technique for more efficient of your parallel results. It's your you use this MPI technique and you have a better results in computational time or in accuracy of your solution?
No, it won't affect the accuracy. It's about computation time, of course, because when we switch between the technologies, actually we should solve the same problems. So we use the same, of course, we, for example, can go from double to float, then we'll have different accuracies. But in this case, it will be just, the algorithm should produce the same results, but faster. That's it.
Okay, it's good. Thank you very much for your talk. And now it's time for a break for lunchtime. And after 1 hour and 10 minutes, our day session will continue. And join to us and go to the lunch. Thank you very much.
Thank you.